as well. Uh, Hello everyone. My name is Shuchi. I'm a power systems engineer at the Pacific Northwest National Laboratory. I have been at the lab for around 5 years now, and a lot of my work focuses on using measurement, uh, on developing measurement-based applications uh, that can improve grid resilience, grid reliability, that sort of things. And today, I'm going to talk about some of our recent work on oscillation detection and characterization using quantum wave measurements. And the work that I'm going to talk about, it has been funded by the DOE Office of Critical Minerals and Energy of Innovation through the Optima Award. And Jim Follum at PNNL, who is also on the call, he's the lead for the project. I'll start with a description of the big picture that like the algorithm or the approach that I'm going to talk about, how that fits into the big picture of the Optima project, and that will uh, showcase some of the motivations of why we took a particular approach uh, the way we did. Over the last few weeks, there has been quite a few presentations in this task force on how PME data is limited in being able to accurately capture and monitor the high frequency dynamics of power electronic interface loads and generators, and how you can only capture low frequency modulations of the feature using PME data. And this motivates the use of quantum-based measurements to get more granular insights. But then that comes with some of the practical implications that it is like really not feasible to stream continuous quantum wave measurements up to a central utility coordination and then doing downstream analysis. So this limitation um, not only would be cost prohibitive, but also it would just take a lot of time. So, mm, uh, uh, updating all of the communication frameworks within a utilities backbone network, like probably not a low effort approach. So to avoid this heavy lifting, something this motivates some edge processing that you look at all of the streaming point and wave measurements coming at the substation level, analyze all of the measurements at the edge itself, and then that if there is any interesting things happening in the point and wave data, so some of those analysis output, if that should be notified and that might be relevant for operations, that can be streamed up to a central coordination level for further analysis and maybe a wide area view of how maybe different IBRs are responding, or different generators in an area, generator storage load, or whatever they're doing. So that kind of a wide area view can be enabled at the central location itself. So through the Optima project, we are developing such a distributed measurement-based platform. The platform is being called WaveApps, and this is being developed by the Grid Protection Alliance. And the idea is, again, like, you would have these WaveApps field instances at different substations monitoring some of your IBRs or other generation and load resources. And then these WaveApp field instances will have a few analysis applications built in, and then they will be the results of the analysis will be streamed upwards for central coordination. And the streaming requirements will be comparable to that is required by PMU data. So then, an overhaul of the communication infrastructure is not required. Within the WaveApps project, we are developing 4 applications, but then the platform itself will be extensible. So any other applications that we develop in the future that can work on point and wave data, these can be integrated into the WaveApps platform as well. So within this project, the 4 applications that are being developed are oscillation correlation analysis, and this is the one that I'm going to talk about today. But oscillation source localization is being developed by the University of Texas at San Antonio. And then PNNL is also developing a nuisance strip detection application. And then GE Vernova is developing a grid strength monitoring application. And all of this will be demonstrated at SRP. So we are really excited about it. So what does the big picture of what the oscillation correlation module want to do? How does that look like? There has been a lot of development on the oscillation detection piece and the source localization piece. But there also is one step further than that, like what caused being able to determine where the oscillation is coming from is not the end. We also want to know, ideally, like what caused the oscillation. If you look at a lot of the root cause analysis, uh, ad hoc root cause analysis that are performed after a particular oscillation is observed. A lot of that involves just looking at what happened uh, in the system during the oscillations, preceding the oscillations, and that can probably provide clues on the phenomenon that caused the physical phenomenon that caused the oscillation itself. And a lot of field instances have also pointed to the fact that, say for IVRs, if the parameters are not properly configured, there can be very low amplitude oscillations that are existing in the system. But because they are low and they are not causing wide area concerns, maybe operators do not know about it, or even if they know about it, they don't do anything about it. So that kind of hidden risk persists in the system, and then if like some event happens or a particular type of scenario happens in the grid, then these oscillations can get amplified and cause much larger reliability problems. Uh, but perhaps if someone had diagnosed the presence of these latent configuration issues through the presence of these low amplitude oscillations, then they could have done something about it earlier or fixed some of these configuration issues so that, the hidden vulnerability did not persist in the system. So this is the problem statement that we are trying to uh, address with this oscillation correlation module approach. And how we are planning to do it is, you can see from the flow chart I have on this slide. So there will be a large number of VWAPS field instances deployed in the different substations in the system, and they will be constantly running. So they will be detecting system conditions, changes in system conditions continuously using phasor data. Things like if the uh, 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 P or Q output coming off the substation that it is monitoring, whether that changed, whether there was a grid disturbance, whether there was a substantial change in operating conditions, whether there was a change in topology. So things like that. And then it will also be running oscillation detection and characterization modules in real time, so that when an oscillation is detected, the field instances will report up to the central location that there was an oscillation detected. This is the frequency, these are the amplitudes, and whichever location has detected that oscillation will also be sharing the same information with the central instance. And then the central instance will aggregate data from the multiple sites and see whether there was a change in system conditions just before the oscillation onset, or if there was a change in system configuration during the oscillation window, and whether that changed the properties of the oscillation observed or not. And then it will try to establish a correlation that maybe that there was a uh, change in active power input from a particular plant. And within 2 seconds of that set point change, oscillation started happening. And as the plant was ramping up, uh, the amplitude of the oscillation started growing as well. So this would result in a high confidence correlation. And something else which is unrelated, maybe like there was a change somewhere, uh, like 7 seconds before an oscillation started, that would result in something which is of low confidence. And then it will also determine whether something like that has been observed before or not. So if you see Low confidence correlation recurring, maybe it has happened like 7 times within a month or something like that. Then that can be included in a report for someone to go and check that, maybe like we cannot tell you exactly what is going on, but there is this recurring problem in this location that warrants a closer look. And I also want to say that, like correlation is not equal to causation. So we cannot uh, uh, like really promise that the output from the module will give you an exact root cause analysis, but it will be a step in that direction. It will streamline the initial uh, uh, the process, the initial methodology itself, and then and make it easier for someone to see what was going on throughout the system, and that can make the root cause analysis more streamlined and faster. And on the bottom of the screen, you can see an example of how we plan the visualization to look like. So here, what is happening is there are three sites which saw an oscillation, and then there was site A, which had a power ramp just uh, preceding the oscillations, and then the power ramp persisted throughout the oscillation observation period as well. And you can this is judged to be a high confidence correlation because this rule that 0.62 hertz oscillation following a P ramp at this particular site has been seen 5 times in the past from the same location. So that would suggest that there is a correlation between that, every time this plant ramps up, there is an oscillation in the system. So this could indicate that there is something within the configuration parameters of the plant itself that needs to be looked at. All that to say that, a lot of the accuracy of all these downstream applications to be able to make a correlation module depends on fast and accurate oscillation detection and estimation. And because we are looking at uh, because we are trying to detect oscillations that can be of low amplitude and do not last very long. Uh, so this being able to accurately isolate the oscillation components from just ambient point on the wave data is important. Uh, so as I said, because we are trying to build this application within a distributed edge processing system, there are some particular design constraints that we have to think about. So the first one is uh, we know that a lot of the high frequency oscillations have been reported by industry, but if you go and look at some of these reports, a lot of the times the uh, the presence of the oscillations were not detected by any like point on wave device. It was more that that the presence of a high frequency oscillation probably caused some light flicker, and then you customers called up, and then someone went and investigated and found that there really was some kind of a high frequency oscillation happening due to some IBR operating, and that resulted in this oscillation. Uh, another common theme you will see in industry reports is that someone saw a very low uh, component at an alias frequency in PMU data, and then when they went and then pulled the DFR records, then they could see that a much larger oscillation was visible in the DFR update. But then there is always that possibility that the DFR did not get triggered, and then that uh, period of oscillation was not recorded, and so now you don't have anything to analyze. And I think Ben mentioned this for one of the Kauai Island oscillation in his presentation uh, 2 months back. So all of that to say that again, oscillation detection methods using real-time oscillation detection methods using continuous point and wave streams are a need. And now to build this onto the VREFs platform, there are three main factors that we wanted to keep in mind. The first was computational efficiency. So we did not want to necessarily come up with the best and most sophisticated method that would require like heavy mathematical operations that would require higher processing higher computational requirements because the field instances of the Wave Apps platform is intended to run multiple applications concurrently. So a lot of the analysis infrastructure will be distributed across multiple applications. So we wanted something that was practical, fast, and low computation requirements. So that has motivated a lot of the design choices that we have made with the algorithm. The next is that the spectral leakage problem due to off-nominal, due to the power system frequency that can be not exactly 60 hertz and it can move around and it can also, it is not stationary. So being able to extract the oscillation components from that will be important if we want to diagnose the really low amplitude oscillation. And then we also, like it is difficult to extract low frequency oscillations from point on wave data because the spectral components are too close to the fundamental. So we understand that, maybe like signal processing can be done to extract those low frequency components, but that basically boils down to almost like recreating PMU algorithms. So PMU data might be better suited for the low frequency oscillation detection and analysis. So we would probably need some kind of a multi-resolution, multi-time resolution approach to be able to cover the entire frequency spectrum of oscillations. But we still want to come up with something uh, that is applicable to as high in frequency range as possible. So we wanted to come up with something that would work from 1 hertz upwards to much higher frequencies. So I have tried to illustrate what the problem from the fundamental not being exactly nominal and drifting around uh, uh, would look like from like just a data analysis perspective. So on the left, you see that what if your frequency is exactly 60 hertz or 50 hertz, and then you have that knowledge a priori, and so the window length that you select is an exact integral multiple of the oscillation fundamental oscillation period. So in that case, you would have a large peak at the persistent frequency, and then you would have the sub and supersynchronous sidebands appearing on either side of the fundamental. So this would really be easy to uh, uh, estimate. But oftentimes, and most of the times, what is likely to happen is that the frequency will not be 60 hertz, or it can also drift around in the analysis period. So you would have a lot of spectral leakage from the fundamental band, and that would uh, that would make it difficult to just isolate uh, the sideband. And here, the sidebands are still visible, but then you can see that, like they have been attenuated a little bit, so it would not result in accurate amplitude estimates. So how we are trying to get around that is using the quadratic spectral interpolation approach. So this is a pretty well established signal processing algorithm. So what this does is it uh, uh, given a FFT, given a DFT, and looking it is searching for the peak. So suppose the because of the frequency resolution of the way you're computing the DFT, you are seeing the frequency content highest at a particular bin, but the actual frequency peak is somewhere in its neighborhood. So how the spectral interpolation technique does this uh, uh, does the peak search is by fitting a complex parabola around the three highest peaks. And this the one limitation of this algorithm is that like it works best when it is like a single tone kind of a signal. But then like if we are expecting that we are just doing the search in the vicinity of the power system frequency itself, so then the results transfer well. So the complex parabola fitting aims to identify like what this fractional correction term would be. So these are the expressions that the formula boils down to. So you will see that like this is just a mathematical computation that like you just take the DFT values of the three peaks and then you have to arrange them. Boils down to arithmetic. So it does not add. It is a computationally very low expense operation. This estimator is unbiased and then it shows best performance for rectangular windows. So we have chosen to go ahead with rectangular windows again. So it avoids the one step of having to do windowing, which probably is not a big deal, but then every computation saving that we do makes the algorithm run faster. And this was one of the motivations that we wanted with that wanted to go with that. We don't necessarily want the best uh, and most precise algorithm. We want something practical and fast that will be robust for real-time implementation and give good results. So the way we are fitting that spectral interpolation into our analysis pipeline is something like this. So we take a streaming measurement window. We do not know what the fundamental frequency is, but we initially assume that it is somewhere in the vicinity of 60 hertz. So we do a FFT with the 60 hertz assumption. So the first FFT will show a lot of spectral leakage. And then we use the parabolic spectral interpolation technique to find a defined synchronous frequency estimate. And then we just adjust the window length so that uh, we adjust the window length so that uh, the window now contains an integer number of fundamental period cycles. Uh, so so we have this adjusted measurement window, and then we can, since we have estimated the fundamental frequency, we can subtract the fundamental estimate from the signal itself, and then recompute the FFT, and that gives us a defined spectral estimate. And then based on whatever detection thresholds that we set, we can detect the presence or absence of an oscillation. There are further improvements that can be made in the detection threshold piece. And this is something that other PNL researchers have been working on. But here, for this work at least, we just set the detection threshold to be a particular uh, uh, percentage of the fundamental component. So if something is like 1% or 2% of the fundamental frequency component, we would call a oscillation detector. So on this figure here, you can see an example of how this how the proposed pipeline helps improve the estimation accuracy of the spectral components. So in this setup, we have the fundamental frequency drifting from the fundamental by zero point 0.1 hertz, which is a little high for normal operations. But like what if there was like a generator trip and then the oscillations persisted during that. So we wanted to kind of take these edge cases into account and see that uh, the, uh, uh, the algorithm performs satisfactorily even during these edge cases. So we have the fundamental frequency at 59.9 hertz, the oscillation frequency at 2 hertz, and then the oscillation amplitude is zero point 0.1 per unit. So you see that the blue trace shows what the frequency content looks like if we are just doing FFT, assuming 60 seconds, sorry, assuming 60 hertz fundamental frequency. And then the black dotted lines are the true values of what the sidebands should be. And then you can see that with the proposed method, we are able to get like really high estimation accuracy. Another thing is like how long should the window. So because we are interested in detecting low frequency oscillations that do not necessarily last for a very long time, we have like chosen to go ahead with a window length of 2 seconds. So the advantage is that like so because this analysis pipelines requires two FFT calculations, which are the most expensive computation steps here. The limiting the length of the window gives us faster computation. And the other thing is that, the amount of frequency fluctuations within 2 seconds, within a 2 second window, would probably be lower. So that would result in a lower spectral leakage that we have to deal with. On the other hand, the 2 second window length approach limits the frequency resolution to zero point 0.5 hertz, which might be acceptable for the the resolution might be acceptable for something that is running real time, but then for offline analysis and for really significant oscillations, maybe you can look at a longer window of data, and that would improve the frequency resolution. So here is an example of how the oscillation analysis pipeline performs with synthetic data. I realize that the plot is a little difficult to read, but the different color bands are showing the same oscillation injected on different fundamental frequency components. So a 1 per unit signal at different frequencies. So 60 hertz, 60.01, 59.99. So we injected plus minus 0.01, 0.05, and zero point 0.1 hertz. And then we modulated those fundamental frequencies with the oscillation that we are injecting. And we synthesized several different signals at 1 hertz, 3 hertz, 8 hertz, and 15 hertz with varying oscillation amplitudes. And the black traces show what you would get the relative error for the vanilla FFT method, and the red traces show what the relative error with the proposed interpolation, spectral interpolation based pipeline. And the errors are plotted in the logarithmic scale for easy visualization. And some of the things that I would like to point out is that in almost all cases, in all of the cases, the proposed pipeline gives like an order of magnitude improvement compared to the baseline FFT-based method. And then some other things that you can notice is that the estimation error obviously increases the more the fundamental frequency deviates from the nominal value, and then the estimation error goes down, at least in the uh, 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 baseline method, if the oscillation amplitude itself increases. So then you can, it is easier to search for the peak. So all of that was about detection. Now to the next component of the oscillation analysis pipeline comes to source localization or participation factor estimation. The participation factor estimation is important because, especially if the oscillations that we are seeing uh, is manifested due to control interactions from multiple IBS, a single source is not well defined, and there might be uh, multiple elements like contributing to the negative damping of the oscillations. So we would like to indicate that as well. So this one of the participation factor estimation formulation was proposed in one of these papers by Pablo Esteves and Slava. So we have taken those expressions as well. And then several approaches based on quantum wave data for oscillation source localization have been proposed in recent years, including like a quantum wave extension of the DEF-based approach. And we have discussed that method, like Slava had a presentation, I think last year sometime, on one of their recent publications that extends the DEF method to the quantum wave domain, and I think Ben is also working on it. Then the interharmonic power-based approach that Dr. Shu presented, There are some publications on super synchronous power based approach, which also looks at what is the active power and reactive power contributions at the sub and super synchronous bands. Uh, so we are not trying to come up with a new source localization approach at all. So we are trying to find ways of computing some of these approaches in the in the fastest and most accurate way possible. So if you look at a lot of these expressions, I have pasted some of the screenshots from these papers, and here you will see the SSO-CDEF expression and then the sub super synchronous power expression, and you will see that um uh, that the that the computational blocks are very similar. That it's like the uh, sub and super synchronous component of the active and reactive powers. So if we can accurately and in a fast manner compute these terms, then implementing any of these methods becomes easier. So that is what we are looking at. And what we have tried to do is eliminate the requirement for real-time automated bandpass filtering. So to do this, what we need to estimate are the amplitudes of the voltage. Uh, okay, sorry, I should have written I over here, but I have made a mistake and written P. But what we need to estimate are the sub and supersynchronous uh, component amplitudes for the voltages and the currents and their corresponding phase difference. So the amplitude estimates are obtained from the previous step, so we don't need to redo it. So we gain some computational advantage by reusing results from the detection step itself. And then the phase differences are estimated using the cross-spectral density between the voltage and the current waveforms at the sub and supersynchronous frequency bin. And then again, another computational advantage we gain here is because we have already computed the FFTs of the voltage and current waveform in the previous step, so we can just reuse that. So I think the only operations required would be a complex conjugation and then a matrix multiplication. So basically, we get a fast and accurate pipeline for being able to diagnose, uh, being able to accurately detect and estimate oscillatory components in waveform data. So now I'll move on to some of the simulation results. So we have simulated different oscillation scenarios in the IEEE modified 14 bus system. This is a very similar setup to the paper that Slava had written. And we basically looked at their reference and went to the GitHub repo and took that Simplus. It's a MATLAB-based tool called Simplus. It's open source, and we took that scenario and modified it to inject oscillations based on our requirements. So the results from this work is scheduled to be presented at the upcoming SDSMA conference. So in that paper, we have only looked at forced oscillation scenarios, but then we have also been um, uh, simulating different control interactions that, like we try to tune the control parameters of the inverters just so that a step change at a particular inverter or maybe a grid disturbance would uh, like activate one of these control interactions, and then we would see growing oscillations because of this control interaction. So we have simulated several of those scenarios. Uh, for this particular paper, what we did was we created 27 scenarios of sinusoidal modulation in the inverter set points. It's a combination of three different frequencies and then three different amplitudes. So 1.5 hertz, 5 hertz, and 15 hertz. And the oscillation amplitudes were 1% of the fundamental, 3%, and then 5%. And then we also created three additional scenarios where the modulation function was a square wave at again at different frequencies and one amplitude. So we had a total of 30 different forecast solution scenarios. And then using our analysis pipeline, we computed the DEF and the SSP terms for each of the 30 scenarios. And we have not done the complex DEF expression. It was just the like basic DEF where we are only looking at the P plus and P minus terms. And for each of these cases, if we look at the results and say that the location with the most negative term is considered the source, if that is the approach, then both the methods achieve 100% accuracy. But if because we are looking at it from like a distributed implementation perspective, and if we want to see that any location which is having a negative GEF term or a negative SSP term, if we term those as potential sources, then the accuracy degrades a little bit. Then the accuracy degrades. The DF accuracy becomes falls from 100% accuracy to about like 84%, and then the SSP accuracy reduces from 100% to 62.5%. So there may be like relative strengths and weaknesses of the methods, but again, like the message here is that they all build on the same computational blocks, and that is what we are trying to estimate. So I have a couple of examples here. So this is from two scenarios and two particular 2-second windows. And as you can see, so the top panel shows the frequency injection at 15 hertz. The oscillation is at 15 hertz. And A12 is the source where this oscillation is injected. And you can see the that both the sub-super synchronous power and the DEF methods correctly point out A12 as the source, and then uh, its negative contribution is far above the other three inverters which have negative DEFs. But like if A12 was not observed, then probably we could get some misleading results. Then the bottom scenario shows when the oscillation frequency is at 1.5 hertz, and here the forcing frequency is close to one of the natural modes. And so we observed that with the DEF method, the DEF method outperforms the SSP based approach. So you see that A12 is the only location high with negative TF terms, but in the sub and super synchronous approach, there are multiple units which have like comparable negative terms. Some other just from uh, how stable are the estimation, that kind of perspective, and looking at some visualization results. So here we are seeing what the outputs would be from the analysis pipeline. Uh, and here we have implemented it on like 2-second sliding windows and with like 1 second overlap. So the windows are going slid forward by 1 second at a time. And you can see that the different like subplots are showing whether the oscillations are detected and what frequencies they are detected at. The blue the blue circles indicate that both of the sidebands are detected, and then the orange circles indicate that only one sideband was detected. So this might be possible because the particular scenario that I'm showing here, it was like 1% amplitude, so it decayed. It was not very high amplitude at certain points in the network, so it was below the the detection threshold for some of the components. So only one sideband. And we are using some of these checks further down in the pipeline to basically indicate how robust our detection results are and what could be real versus just measurement artifacts. And then on the right-hand side, you see how the estimation of DEF and SSP across multiple streaming windows, how that varies. So you can see that, like in the first few windows, the estimation settles, and then across the next few windows, the values are pretty stable. And then talking about computation time, the time axis here is in milliseconds. So we estimated, or we computed what the computation time for each of the 2-second windows is going to look like. So you can see the distribution. It goes from like 20 milliseconds to about 132 milliseconds in some outlier cases, but the median computation time is around 34.25 milliseconds. And this is with like my non-optimized coding on my personal PC. We hope that when we actually transition it to an application on the web apps platform, we will further uh, like tighten the coding approach itself. So hopefully that will be faster. But then like right now, the computation time seems suitable for real-time implementation. Uh, Future directions. So, like Dr. Mani had the presentation last month about the value of having some of these um, oscillation simulation data sets publicly available for just benchmarking different algorithms, and so that that the community does not duplicate efforts of just treating models and simulating the oscillations. So we, as I said earlier in the presentation, we have been working quite a bit on simulating not just forced oscillations, but also some of these control interactions. So this is something we are looking at, that making some of these simulated data sets publicly available. We see opportunity in defining the detection threshold. That is something we will pursue. And then something we have not done so far is checking the robustness of the algorithm with realistic noise and realistic data, like how the noise is in real point on wave data and how that will impact the entire analysis. And then next year, there is a demonstration of the web apps platform scheduled at SRP. So we are really excited about that, and hopefully we'll get some good results from that demonstration period as well. So that was my presentation, and I'm looking forward to feedback and questions.